Hi everyone, my name is Michael Glushakov and I'm a junior at Duke University studying computer science and computer engineering. And today I will talk to you about edge-based provisioning of holographic content for contextual and personalized augmented reality. Or if you wanted to say it in 2 words, how to use edge computing to make AR better. So first we'll briefly go over the current state of augmented reality and the current state of edge computing, and how the combination of these 2 technologies will lead to better AR experiences. We will then dive in 2 case studies. We did one for Google AR Core, which is one of the most popular AR frameworks for Android phones, and one for Magic Leap 1, which is one of the most popular AR headsets on the market. Finally, we'll talk about the challenges posed by the current state of AR and the potential directions for how to overcome them. So in augmented reality, the virtual content is laid out around the user in the same spatial coordinates as the physical objects surrounding her or him. The pictures below show the examples of currently available AR experiences. The first picture is used by furniture sellers such as IKEA or even Amazon to show their products in the same physical space as the user. The second picture shows a feature that was recently added to Google Translate, where any text can be translated to the language of users choosing, and the translation will be overlaid over the original text. Finally, the third picture shows a gaming experience built in real world that we developed in our lab. So the big tech companies seem to agree that AR devices will change the way we interact with technology in a similar magnitude that the iPhone did back in 2007-2008. By the way, if you can't see, the picture behind Mark Zuckerberg is a 10-year roadmap of Facebook's priorities, and it shows VR and AR as one of the top pillars that the company will focus on in the future. So now that we're done with AR, let's talk a little bit about edge computing. You currently may have heard of cloud computing, where you have several large data centers filled with powerful servers that do a lot of the computation and offload a lot of the computation from the client. Edge computing takes this idea of offloading work to the server and does it slightly differently. In edge computing, you have many smaller data centers with servers called cloudlets, which are physically located closer to the user. Currently, the internet service providers are thinking of putting them at every cell phone station. So the closer physical proximity allows you to save time on how long it takes for data to get to and from the server, and as a result, it is good for some applications which require a lot of computation to be done fast, such as smart cars, self-driving cars, the Internet of Things, medical devices, robotics, etc. AR requires a lot of data to be used, and the phones and the headsets that run AR frameworks are not necessarily the most powerful, so they can benefit from being used with edge computing. So, as I just talked about, current AR is already very impressive but still limited. There are issues with battery life, computational power, and space, and the potential solution is offloading some of the work to the server. This doesn't really work with cloud servers because the large physical separation will lead to long latencies and long delays for the user, to the point where there is no point offloading the work to the server anymore. With edge and fog computing, the servers being located closer to the end user will allow to actually reduce computation delays. It will also allow us to access some local sensors in the area that will provide more information about the user, such as user location, and that will allow for a more meaningful AR experience. So we're currently developing such a solution for Duke Lemur Center. For those of you who don't know, Duke Lemur Center has the largest and most diverse population of lemurs outside of their native Madagascar. It is a world leader in the study, care, and protection of lemurs, and hosts both researches and public tours. We believe that edge-supported AR can help enhance the user experience at the Duke Lemur Center by offering personalized holographic content. So as we discussed before, device storage is limited, so when you're building AR app standalone, you can really only afford a small number of models. However, when the models are stored and loaded from the server, you can suddenly download and use a lot of different models, and that allows for a lot of personalization. An example of personalization would be looking at the age of user, native language of user, or the current weather. We're also able to leverage additional local sensor data to inform the server of which model should be chosen. So for example, it gets really hot in the summer in the Duke Lemur Center, so we could have sensors, temperature sensors, which when the weather gets above 90 Fahrenheit will tell the server to send a animated helper that will tell people to stay hydrated and drink lots of water. In terms of different aspects of the user, as you can see in the picture before you, there is a lemur skull. This would be more appropriate for someone who is a senior researcher or an adult, versus a child might see a animated lemur that tells them fun facts about lemurs and entertains them that way. So there has been some related work done in this area. There has been a lot of work done in context-aware AR applications. However, this work has not considered how to obtain holographic content in the first place. There has also been work done on-demand loading of 3D content, mainly supported by the video game streaming platforms such as Xbox, PlayStation, and most recently Google Stadia. However, this type of work is not optimized or examined in edge conditions. Finally, there has been some work on generic edge computing and edge caching. However, we are the first to develop edge-based holographic loading framework for common AR platforms. So now let's dive into the AR Core case study. Just to reiterate, AR Core is the top AR framework for Android, built and developed and supported by Google. The motivation behind this case study targeted museums and zoos and other public spaces, which might greatly benefit from an AR experience but might not necessarily have the funding to hire developers to build custom applications. We solve this problem by offering code-free AR experiences. Our API was built in Node.js with MongoDB as a database, and our client is an AR Core-enabled Android app. However, this could also be extended to Apple's AR framework, which is ARKit, as it also supports image overlaying with models and runtime loading. The only difference is the file format used by Apple's framework. So this is the API overview. In green, we can see the flow for the client, where the client is a museum or a zoo. First, they have to upload the images that they want to use in their experience. They will then select the model determination script, which is based on weather, age of user, language of user, etc. This script creates a series of conditions and key value pairs, where the key is the script output, script condition, so sunny or rainy or child or adult, and the value is the corresponding 3D model. So the final step is for the client to upload their 3D models for each script condition. After that's done, a user who's a museum visitor could download all the images, download the mappings from image to a model, and then their phone switches into the tracking view, where when an image is found by the Google's AR Core image recognition API, a GET request, HTTP GET request is made to the server, and the 3D model loads and is overlaid on top of the image. So we use this API to do some performance metrics. We use the 3 models shown in these slides. As you can see, they're of various sizes. We tested it on both an edge server running at Duke and a cloud server running on Heroku, which is a large CDN. And we used both SFB and GLB file formats. We did not use GLTF for the test because, unlike GLB and SFB, GLTF does not encode textures within it. So this is a summary of our results for download times only. As you can see, we used 2 different phones, Nokia 7.1, which is a mid-tier phone, and Pixel 3, which is a more powerful high-end phone. The columns show different test conditions. And as you can see, the time is overwhelmingly positive, except for the last few rows for a very large file. So what does this mean? We generally have faster load times for edge servers, which makes sense. Edge servers are closer to the user, so the latency is smaller, so it takes less time to download. It's also generally faster for GLB than SFB, which also makes sense since GLBs are much smaller in size. This does not hold for large files. There are several potential reasons for this. One is that latency plays much less of an effect for large files, and their channel width and bandwidth start to take over. The other potential reason is that Heroku is a large CDN, and it might invest in infrastructure that allows for large files to be transported efficiently, versus Duke might not make those optimizations for their virtual machines. Okay, so we also ran a test where we loaded these files, these 3D models, into the file system, and then measured how long it takes to bring them out of the file systems, load them into the program, and then finally process and display them. We tested it for both GLB and SFB, and noticed there is a very large time difference, as GLB takes much longer to process. So the key takeaway from this is there is a much longer processing time from GLB, and if you add up total load time and processing time from the two tables, you get much smaller results from SFBs than GLBs. This is very important because the whole reason GLB and GLTF support was added in the first place is due to high developer dissatisfaction with having to drag and drop their 3D models into Android Studios to generate the SFB files. Developers wanted a format that was supported by big 3D modeling softwares. And so that's why GLB was added in the first place. However, we have found that for any time-critical AR application, which most AR apps are time-critical, you should really use SFB files regardless. Okay, so now we can go into the Magic Leap 1 case study. So AR headsets are a relatively new consumer device that is still at its early stages. However, big tech is set on the vision of AR glasses replacing phones. So it is important for us to look at this category of devices as well. These devices suffer from the same limitations as smartphones in battery life, computational power, and memory. However, it could be argued that the size constraint is even more evident in AR headsets than in mobile phones. A user might be willing to settle for a larger phone that has more power and memory and battery life. However, we would not be wearing helmets on our head rather than glasses just because a helmet offers a more powerful experience. So for this study, we used Magic Leap 1, which is one of the most adopted AR headsets on the market today. Currently, 3D models on modern interactive apps such as video games usually range from a few to a few hundred megabytes in size. AR applications, unlike video games, pose a unique challenge. In video games, the user is constrained to a map or a space predetermined by game developer and can't venture outside of it, versus in an AR application, the user is in the real world and can go anywhere they please. And so that makes it difficult because you need many more models. The model usage is dependent on the user's environment, and it's very difficult to predict which models to load in advance because you don't know where the user will go. A solution to this would be runtime model offloading, where the headset loads models from the server at runtime. So to reiterate, we load the models onto Magic Leap 1 at runtime. We used 3 different models to emulate low, medium, and high model qualities. And for this experiment setup, our Edge server had a 10 millisecond route trip time, away with 50 megabit per second bandwidth, and the Magic Leap 1 was connected to internet with 5 gigahertz Wi-Fi. So this is the summary of our findings. If you add transfer and decompression time, you will see that it takes around 2 to 3.5 seconds to load and process the image, the model, and that is actually quite noticeable for the user in terms of delay. However, from our own experience, We believe that this delay is acceptable as users would naturally try to familiarize themselves with the environment first before they start looking for the holograms in the environment. So this delayed appearance of holograms is not that bad. So we could solve this issue by preloading holograms to conceal this delay. And this can be implemented in two ways, either by predicting the user interaction or recognizing user location. For predicting interactions, we could say that we know that once people enter a particular building, they always turn right and go into a particular room. So we could already preload all the models into that room as soon as the user enters the building. Or for location, even simpler, we just get user's location and load all holograms within a certain radius. There are problems with both of these. For the prediction, there is really no data set on user behavior in AR applications. And for location, the current commercial AR devices do not have sufficient APIs to implement such features. The current geolocation APIs are only accurate up to tens of meters. However, AR might require much more precise measurements with error within less than a meter. We did an experiment by sniffing for Magic Leap's 1 MAC address using Raspberry Pi and preloading holograms once the user entered a particular room, and that indeed did improve the user experience. Okay, so this concludes the Magic Leap case study, so let's now talk about the challenges and future research directions. One challenge arises from when the edge servers are under high stress, either from a large number of users or poor wireless channel conditions, etc. This adds large user-facing latencies. The solution we could propose to this is supplying holograms of different quality levels depending on the conditions of the network. An example of this is shown in the image below, where you see the Stanford Bunny model in different conditions with high, medium, and low resolutions. This would particularly be useful for large models, as they can be substituted with their simple counterparts in poor network conditions. Another challenge is, and future research direction, is proactive hologram transmission. We did mention it before. It does reduce user-facing latency because the user is not there to experience the latency as things are loaded before the user even gets to the spot where he's supposed to see the hologram. And we can also optimize for bandwidth utilization over time. The research directions here is developing caching and eviction policies, as well as leveraging user locations in hologram transmission. Okay, so today we talked about how edge computing can be used to improve current AR experiences. We proposed to personalize AR experiences by using edge servers to transmit appropriate holograms to the users. We showed you several case studies that we conducted on both top mobile and top AR headset platforms. We identified challenges that arose from those case studies and discussed future research directions that could help us solve these problems. All of our code is available on GitHub. We would like to thank the Lord Foundation of North Carolina, the National Science Foundation, and Stanford, CG Trader, and Kronos Group for their 3D models. If you have any questions, please feel free to email me at this email. Thank you.